Hello. Let's look at sensitivity analysis for linear programming. So this is just an intro linear programming course, and we've spent some time introducing the idea of sensitivity analysis. So I just want to remind you of what the main goal is. We'd like to just see how far we can push a parameter, and then we want to see how far it can go while staying optimal and feasible at the current basis that we're at. Okay. Now, if you're looking at a simplex table, to check optimality, all you're looking at are the reduced cost. You don't care about the objective function value. You don't care about the body of the simplex table. All you are looking to see if there's any attractive variables to enter. And if there are no attractive variables, then we're optimal. So if I'm checking optimality and I see how far a parameter can move, all I need to check are the reduced cost. As far as feasibility, the way the simplex algorithm works, if I just keep everything non-negative on the right-hand side, these are what the variables that are in the basis will be equal to. As long as I keep these from dipping into the negatives, then I'm staying feasible. So when performing this basic, for this intro level stuff, sensitivity analysis, I'm only going to need to keep my eyes on what the reduced costs are and what the right-hand sides are. And lucky for us, these have very simple, well, at least somewhat simple. These have formulas to find. I can make changes and use these formulas, which are just vectors and matrices being multiplied, and to check and see when they're greater than or equal to 0. Okay. Now in this class, like I said, this is an intro linear programming class, so we're only going to look at changing objective function coefficients, both basic and non-basic, and right-hand side changes. And these are natural changes that occur in the real world, because these coefficients in the objective function are things like the profits you're making off of stuff, and that can change with market demands, and that can change with pricing really easily. There's a lot of flexibility built in there. And these right hand sides are things that are limiting our constraints. They may be something like, in context of a problem, like the amount of employee work hours you have, or the amount of raw materials you have, and those things can change as well. They may have other effects on changing pieces of the problem, but those usually are more flexible than you realize. Other types of sensitivity analysis that we could do, we could add and change columns, we could add new variables, we could add new constraints, and we're not going to look at those. They're not that difficult, but just for an intro class, these are the easiest ones or the beginner ones to look at. So let's actually jump into an example, okay? And show you what I mean, keeping in mind these formulas. So if I jump into this LP, so here's an LP, and all we need is what's the optimal basis. So the optimal basis contains x2 and s2. Those are the basic variables at the optimal. And this is the original table. That is all I need to perform sensitivity analysis. I need to know what the optimal basis is, and I needed the original table. Okay. Now, I can do a lot more than this with sensitivity analysis. Quite often in higher levels, we will perform sensitivity analysis on one of these parameters, and we would like to see what the optimal is for the entire range of values. But in this intro course, all we are doing is looking at, while staying at this basis, how far can I push this parameter before I am no longer optimal or feasible. Okay, so a few things we need from looking at the original. The easiest pieces to rip off are the A matrix. That's just the coefficient matrix, the body of the table. I just copied it down. The cost matrix, that's just as simple as ripping off all of these. Now remember, these are opposite signed because we put them in row 0 form. They're just been subtracted over, but 2, 3, 0, 0. The cost on the basic variables in the basic coefficients, that depends on what these basic variables are. And since we said x2 and slack2 are the optimal basis, this is where these columns here are where we're getting this B matrix from. 1, 1 in this column and 0, 1 in that column. And then if you look at the cost on the basic variables, the cost is 3, because remember these are opposite signed, and 0. So getting the basic cost and the basis coefficient matrix come off of knowing what variables are in the optimal basis. The right-hand side is pretty self-explanatory. We have 10 and 12. And then the only thing we'll have left to do then is just invert this matrix B to get B inverse. And that's all we will need to be able to perform this basic intro sensitivity analysis. So let's start with sensitivity analysis on C1. So on the first cost here. So this is a non-basic cost. This is the most boring, simplest type of sensitivity analysis. We would like to know how far we can push C1. Well, C1 is originally 2, so what we would like to replace it with is 2 plus delta. The reason for that is we're saying delta is any amount of change, so 2 plus or minus this change, well, I guess I should say plus this change. This change can be negative or positive, and we will see how far this change can be pushed. And so to check changes to a cost, if you go back and look at those formulas, the right-hand side formula does not have C in it at all. So feasibility will not be affected by changes to C. Only optimality will be affected by changes to C because that appears in this formula. So that's the only formula I will have to check. And so if I put in all these pieces, I have the basic CB, B inverse A, minus C. Now notice the only difference here is I've replaced 2 with 2 plus delta. And then it's just a matter of matrix algebra, right? Matrix arithmetic, not even algebra, matrix arithmetic. So I multiply this vector times this matrix, I get 3, 0. Then I multiply this vector times this matrix, I get 3, 3, 3, 0. And now I can just do subtraction. Subtraction of vectors is just element-wise. 3 minus 2 plus delta is 1 minus delta. 3 minus 3 is 0. 3 minus 0 is 3, and 0 minus 0 is 0. So now, to stay optimal, all of these need to be unattractive. They all need to be non-negative. So all I need to do is this, and this are never going to be non-negative. They're 0, 3, and 0. Those are greater than negative numbers. So all I need to do is just check when is 1 minus delta greater than or equal to 0. We'll just solve that, and it is when delta is greater than or equal to 1. So if C1 is 2 plus delta, and delta can only go up to 1, and then it can be anything less than, well, if this is all the way up at 1, C2 is allowed to go to 3 and can take any value less than 3. So we are allowed to have C1 less than or equal to 3. Okay, so to keep the current basis optimal, C1 must stay less than 3. So that was easy. That's the easiest type of sensitivity analysis, is to perform it on a non-basic cost. It's pretty simple. Let's do one that's more interesting now. Let's do sensitivity analysis on C2. And if you go up and look, C2 is a basic cost. Okay, we're going to replace this 3 here with 3 plus delta. Now, why is a basic cost more interesting? Well, that's because C2 appears in the cost vector, but it also appears in the basic cost vector. Okay? It also appears right here. So I'm going to replace both this 3 and this 3 with 3 plus delta. So I use the same formula again, and notice I have 3 plus delta right here, and I will also have 3 plus delta right here. So it appears twice in the formula. But this just takes, once again, some carefulness. We'll go slowly when I multiply this vector by this matrix. It works out to almost be like multiplying by an identity. It doesn't change. Then multiplying it by A, and this is what we get. Then I will subtract this off. And here we go. 1 plus delta, 0, 3 plus delta, and 0. A few things to notice. Every time we do this, notice that the basic cost, even with all these deltas in there, these basic reduced costs are still zeros at this optimal spot, okay? That's what we want, that's what we should expect. Now, from sitting here, I see that I have 2 elements in my matrix that I wish to check. I need both of these. Every element needs to be non-negative so that I have no attractive variables to enter the basis. So I would like to check that both of these are greater than or equal to 0. And when I solve, I get delta is greater than or equal to -1, and delta is greater than or equal to -3. Now, one of these is more strict than the other. One of these is redundant, since they are facing the same way. These inequalities are both greater than or equal to inequalities. One of these is a little more strict than the other, and that's the one we'll take. I think I have that written here. The most restrictive one is delta greater than or equal to -1. So the cost of 2 was originally 3. And all that it can change is it can go down by 1, but it needs to be, whatever we're adding to it needs to be more than that. So cost 2 can be 2 or higher, and it will the same basis will be optimal no matter what values above this. Okay. Now, last but not least, let's do sensitivity analysis on our right-hand side. We'll use B1. If I scroll back up, you can see that B1 is just 10, so we're going to consider 10 plus delta. Now, this formula is really simple. It's only a matrix times a vector, B inverse times B. And 10 plus delta happens to only appear in the top of this one vector. So when I multiply these, this is what I get, just a matrix times a vector. I get a vector back. And I look here, I have 10 plus delta and negative delta plus 2. Now, both of these, to stay feasible, I don't have to worry about optimality. I only have to worry about feasibility. And so I need these to be non-negative. It's kind of the same thing we're checking. We're just checking right-hand sides. So let me check when this is greater than or equal to 0, and let's check when this is greater than or equal to 0. And we get delta's got to be greater than or equal to -10, and delta's got to be less than or equal to 2. Okay, so we can go down by 10 or up by 2. Well, what was the right-hand side B1 originally? It was 10. So if I can go down by 10, I can go down to 0. If I can go up by 2, I can go up to 12. So the right-hand side needs to be in between 0 and 12. If I keep this between 0 and 12, then I'm going to stay feasible at this current basis. Okay? The idea there is if I push out of feasibility, then that basis cannot be my optimal because I cannot pivot to infeasible points if I'm following the simplex algorithm. So if I go beyond this, then that same basis will not be my optimal because it is not feasible. I have moved this constraint far enough so that I have chopped off this point that was optimal where I had x2 and slack 2 as the basis. Okay, so that's just really simple sensitivity analysis. At higher levels of linear programming, you will do a lot more than that. You will probably want to report on a whole range of values. Shadow prices, when we're looking at right-hand sides, are extremely important, but I will show you an easy way to do shadow prices when we start looking at duality without having to do too much hard work to think about through what shadow prices are. So, but anyways, that's all I have for you today.